It's a great pleasure to welcome you all to the first of the faculty lecture series, lectures in computer science.
The second for this term.
Is it the second?
For this term, yeah.
Oh, okay. It's the second. I've been away, so I'm excused. I'm Alan Mackworth, and I'm not really here, but you can help. It's a pleasure to welcome David Poole. David's a professor in computer science. He's very well known for his work in logic and probability, the two main approaches to doing artificial intelligence. He's been working for quite a while on combining them, and he's having a lot of recent success. He's worked on assumption-based reasoning, diagnosis, ontologies, semantic science, lots of exciting topics. He's co-authored 2 AI textbooks. He's a fellow of the Association for the Advancement of Artificial Intelligence. He's the chair of UAI, the World Organization on Uncertainty of Artificial Intelligence. And he's received the Kayak Lifetime Achievement Award, the Canadian AI Association Lifetime Achievement Award for all his many achievements. And today he's going to tell us what I did on my sabbatical. He was at Oxford last year as the Lever Home Trust visiting professor. He got a lot of great work done on logic, probability, and computation, statistical relational AI, and beyond. David.
All right. Thank you, Alan. All right, so what I'm going to do today is, is that loud? Okay. What I'm going to do today is I'm going to talk about some work that's been going on sort of for almost 20 years now about combining logic and probability. There's been lots of sort of recent interest in it with lots of work on what's now become known as statistical relational AI, and it was one of the first probabilistic programming languages, and we'll talk about that as well. So what I'm going to do is I'm going to talk about combining logic and probability, talk about 2 different sort of ways of doing this. One of just is a very general way of relational probabilistic models. Then we'll talk about probabilistic logic programs. We'll talk about some work that's been going on in what's so-called lifted inference, which is combining some work with probabilistic inference with theorem-proving type techniques. Then we'll talk about some interesting cases of undirected models, directed models, and weighted formulae that we've been doing recently, and some of the things that we still essentially have no idea how to solve with existence and identity uncertainty. There's a whole lot of work that's been doing in sort of first-order predicate calculus, and there's a whole lot of arguments in artificial intelligence claiming that first-order predicate calculus is, in some sense, a good formulation of reasoning. And the idea is that the world we want to represent is made up of individuals, which are just things, entities, objects, and relationships amongst those. And classical first-order logic lets us represent individuals in the world, relations amongst those individuals, conjunctions, disjunctions, negations, and quantification. So the first-order predicate calculus is one of the foundations that we're going to build upon, and there's been a whole lot of work for a while ago about people arguing for this is sort of some sense a good representation for doing artificial intelligence. There's been another community of people who've been working on probabilities, and there's lots of good arguments for probabilities, and one of the arguments is there's lots of uncertainty about the world, but you still need to act even though there's uncertainty about the world. And you need predictions in order to decide what to do, and there's a whole lot of ways that people could build predictions. There are definitive predictions. You'll be run over tomorrow, but you should never believe one of these definitive predictions. If you believe you'll be run over tomorrow, you'll act recklessly, and you probably will be So if you believe you won't be run over, you'll act recklessly, and you probably will be run over. And if you believe that you will be run over, you'll probably be so constrained to not do anything that you won't be run over. So it'll be self-defeating prophecies. You can have point probabilities, some particular probability if you're careful, and some smaller probability if you're not careful. Or people are also arguing for probability ranges. And so what happens, so you could say there's some probability in some range, but the argument that usually comes down to is that acting is gambling, and agents who don't use probabilities, which means point probabilities, will lose to those who do. The so-called Dutch books that actually say, the theorems that eventually say that if you're using probability theory, if you're not using probability theory, you will lose to someone who does. in gambling. And acting is gambling. Whenever an agent goes around and does something, it's gambling. Whenever your Google car drives around, it's gambling as to whether someone's going to jump out on the street or not. The other advantage of probabilities is it can be learned from data, and Bayes' rule specifies how to combine data and prior knowledge. So what we're going to do is we're going to talk today about how to combine these two. So both of these you can see as the foundations of propositional logic. We can sort of go by adding logical variables and quantification to the predicate calculus, or we could have measures over possible world and conditioning to go to probability, but we want to combine these two to get to what's called relational probabilistic models. So we want to have both logical variables and quantification as well as measures over possible worlds and conditioning. So we want to have both the advantages of both things, because we want to talk about relations, we want to talk about objects, relationships amongst objects, but we also want to make predictions under uncertainty. So that's what we're going to do today. Should be familiar with Bayes' rule. The probability of the hypothesis given the evidence is the likelihood times the prior divided by the normalizing evidence. And if you see textbooks, you'll find the evidence is sort of simple conjunctions of formulae. If you might have, now people have images as evidence, you're conditioning on some image or some sentences. But we want to look at different cases. We want to look at what if the evidence is a patient's electronic health record. So the sort of examples we want to look at are things like the evidence that we're going to do is we'd like to input someone's electronic health record and make a prediction about the effect of some drug on that patient. Because that's what you need to effectively do proper evidence-based medicine. And it's going, current, medicine is what, 30% of the world's economy. It's, it's sort of the biggest. If you want to make money, you want to get into doing medicine and doing these things. So you want to condition on a patient's electronic health records. But what if these are the electronic health records for every person in the province, right? You also want to condition on this because we want to condition and learn from these things. So what happens if E is a collection of all the student records in the university? What happens if E is the description of everything known about the geology of Earth? The bottom one's interesting because you can actually find people are now publishing descriptions of the geology of everything known on Earth. It's now being published. There's a One Geology website that people are actually publishing a description of the whole geology of the Earth and would like to condition on this geology of the Earth to make predictions about where to find minerals, where to find landslides. So one of the examples of doing this is some work we did for a while ago with Clinton Smythe from GeoReference Online. Is this is the sort of thing we're conditioning on. We're conditioning on a description. This is part of the Howe Sound. The road up to Whistler goes through there. And so this is sort of, we're conditioning on this knowledge about slopes. We're also conditioning on other parts. So this is a map of the same area, but it has objects. It has faults and folds and all these other and all different geological structures. We like to condition on this to make predictions about landslides. So this is the sort of thing we want to condition on. We want to observe the world that's made up of objects, relationships. It's made up of continuous valued things. We'd like to condition on this in order to make predictions. All right. So that's what we're going to try and do. So we're going to start talking first of all about what's called relational probabilistic models. So when we do machine learning, they typically assume we have sort of these informative features. So if you have this feature construction, for example, is a way of doing, of a hot topic now in sort of machine learning about how can we automatically construct features. But often the values of features are names of individuals, are not sort of features we can use for learning. So it's the properties of these individuals and their relationship to other individuals that need to be learned. And it's often been studied under this umbrella called inductive logic programming because the representations were traditionally logic programs. So I'll give you an example of doing this. So here's an example of a nice relation. There's an individual property value triples, and if you stick this into your favorite machine learning program, they'll fail miserably because the values here are names of individuals, right? The names here is Joe likes this particular resort, and resort 14 is of type resort, and it's of near some particular name of some beach. And what you'd like to do is you'd like to know something about resort 14 in order to be able to predict why someone likes it. So these are the sort of things that if you put this in a typical machine learning framework, it fails. But what we'd like to do is still make predictions about what Joe likes. And the sort of things that Joe likes would end up being something like this logic program here, that Joe likes some R if R is of type resort and R is near some B, such that B is a beach and B is covered in S, where S is a type of sand. So Joe likes resorts that are near sandy beaches is a sort of hypothesis you might come with this. And so from this sort of hypothesis, we'd like to get more structured hypotheses about what we're allowed to do, and it's about objects here, beaches and resorts, and relationships amongst them in order to make predictions about this. So there's a whole lot of work in sort of inductive logic program that gives you logic programs out from databases like this. But we want to make probabilistic predictions. So we'd like to make, not only have relations like this, relational language like this, we'd also like to make probabilistic predictions because we want to make decisions about which drugs you should take, and that requires us reasoning about probabilities. So here's the example that I put up at the start, and which student should do better. Come on, everyone looked at it. And why?
S3. S3.
All right, S3. Is that right? I can't remember. So one of them should, and if you get people coming into first year university, you could look at their average grades, but you probably don't want to do that. You'd actually rather have some probabilistic model that's going to predict grades in here about these relations. So one of the things we can do is we could imagine putting this into a Bayesian network. And here's a Bayesian network for doing this. Is we'd like to have the grades of these students, so this grade of S1, C1 is something we've observed. It depends on the difficulty, of course, C1, and the intelligence or something of student S1. Similarly on the second one here, the grade of course S2, the grade of student 2 in course S1 depends on the difficulty of C1 and the intelligence of S2. And so these all become probabilistically dependent in terms of this Bayes net, as all of these depend on the grades, depend on the intelligence of the students and the difficulty of the course. And we could build a model of this which talks about how in the Bayes net we need the grade depends on the intelligence and the difficulty of the grade of the students in the course, and depends on the intelligence of the course and the intelligence of the students and the difficulty of the course. We could build up some table like this, which has some prior knowledge on the intelligence of the students or the difficulty of the course, and we end up having this, each variable, how it depends on its parents, is the same. We'd like to have some structure sharing because it doesn't actually depend on the individual names, because when we're building this model, we don't know about particular students, we don't know about particular names. So that's the sort of model we're trying to build, is this model that depends on how, sort of probabilistic model like this Bayes net that depends on variables that have multiple parameters. We're going to build up, you could build up this network on the left from this. And if you stick this into something like the AI space toolkit, you'll end up finding that you're going to predict that if you stick this in there and you make observations about all of these grades, you'll end up finding that that S3 on course C4 is indeed higher prediction of an A than grade S, the grade for student 4 on C4. All right, do people get that answer? Okay, so that's the sort of reason we're going to do. And it turns out that by observing that the grade of student A tells you something about the intelligence of student 1, it tells you about the difficulty of C1. And when we observed someone gets an A and a C on C1, it means we don't know whether it's difficult or not. We do know that A is intelligent and the B is not, and that is going, by probabilistic inference, it's going to pass through these, it's going to then do inference to tell you, it's what we saw as the common sense answer in there. And it says that when we're building something, if we're accepting people into first year, we probably don't want to go with their averages. We want to build some more sophisticated model about how to go about predicting how they'll go. And what we're going to do is we're going to write this in some plate notation, we'll call it. And we're going to have this plate notation has students S and course Cs. We're going to think about these as logical variables. We'll explain why in a minute. That represent students and courses. the set of all individuals of some type is called a population, and we'll talk a little bit about population. There's a population here of students and the population of courses. And we're going to have these random variables, which are parameterized random variables, which is the intelligence of a student, the grade of a student on a course, and the D of some C are all parameterized random variables. So we can have these random variables that are parameterized by individuals. And what we're going to mean by this is for every student there's going to be a random variable I of S. For every course there's a random variable D of C. For every student course pair there's a random variable about the grade of that student on the course. And all of the instances are going to share the same parameters and the same structure. So if we implement that for this previous example, we'll find out this network, when we ground it out, here are some of the grades. These are the only ones we need. These are the only ones we're going to observe or query. The other ones we can show are irrelevant to doing this. So I've got this parameterized random variables. And if there are 1,000 students and 100 courses, this grounding contains 1,000 intelligent student variables, 100 DC variables, and 100,000 student course grades. There's 101,100 variables, but it's all with 10 parameters. You have one parameter for this prior for the intelligence of students, one for the difficulty of the course, and 8 students for the probability of the grade given the intelligence in the students. So we have this just like a Bayesian network, but now we have it instantiated for each of these instances. Right. So one more example. Let's suppose we are diagnosing students who are having problems with addition. So the idea is that we're going to give students addition problems. They're adding x1 to x2 plus y1 and y2, and they're typing in z1, z2, and z3. And we can build a Bayes net representation for this. We can say that, for example, z1 on the right there depends on x1, y1, and whether they know how to carry. And this is the Bayesian network, so it also models errors that students can make. There's some random errors inside this conditional probability table. Z2 depends on x1, y2, as well as the carry that goes into it. The carry depends on x1, y1, and whether they know how to carry. Okay, so in this sort of model, we can build this sort of network. So hopefully people know about Bayesian networks for doing this sort of, so we can model this. But then the question is, what happens if there are multiple digits? Well, if there are multiple digits, you sort of want to repeat this on the left for each digit. So we want to keep repeating this for every digit, but whether the student knows how to carry or knows how addition doesn't depend on what the digits. If there are multiple problems, well, the x's and the y's change, but whether the student knows additions or knows carries probably doesn't change by the existence of other examples. The carries and the y's and the z's would change. So if we have multiple students, well, if there are multiple students, the x's and the problems don't change by adding more students, but the students, whether they know how to carry or know how addition depends on the students, and so does the answers that they give depends on the students. And if you have multiple times, then presumably the students, whether they know how to carry and know addition, change over time, but the problems don't change. Here we're assuming the problems don't change over times. What we'd also like to do is to build this model before we know the individuals. So we're not even going to know before we know which individuals, digits, problems, students, and times there are. I would like to build some model or learn it and apply it to new examples. And so we're going to end up with this plate model on the right here, where we have knows carry for every student and time, knows addition for each student and time. For every digit and problem, there's an x. And then there's a carry for every digit, problem, student, and time, and a z for every digit, problem, student, and time. So there are all of these random variables, x, y, x for every digit and problem, y for every digit and problem, knows carry for every student and time, and knows addition for every student and time, and carries for every digit, problem, student, and time. And there is this, the answer, the z, depends on the digit, problem, student, and time. We condition on observing particular z's for particular students and times, and we can do all sorts of inference of finding out whether they know it, and we can learn, and we can actually do a whole lot of learning as well. Because this is the sort of problem that we're interested in. And what we're going to try and do is to have random variables for combinations of individuals in populations. We're going to build these models before we know the individuals. We're going to learn the model for one set of individuals and apply the model to new individuals, and we'll allow complex relationships between these individuals. So we'd like to learn how people, electronic health records, we'd like to learn it from some individuals and apply it to others. We'd like to have a model that exists independently of the people because we'd like to apply it to new people, and so on. Okay. And one of the things we're going to exploit is something called exchangeability, is before we know anything about the individuals, they are indistinguishable, and so should be treated identically. So because we're going to condition on each person, when we have a random variable for a person, they're all identical. When we only condition on the fact things that we know, the individuals who we know nothing about, we're going to treat identically. We're going to exploit this when we're going to do inference and reasoning. When we do this, we have a number of interesting properties for representing conditional probability. The first one is this one we saw before, probably the grade given the student and the time, given the interest of the students and the difficulty of the course. This is the individuals here, the intelligence of the students and the difficulty of the course. They're all going to share these probability parameters because we're going to write this for all students and courses. And so because we don't know anything about the students and course, they're all going to share these parameters. They're so-called parameter sharing. We're going to have some things like here, whether someone's happy depends on whether their friends are mean to them or not, or whether they're not mean to them. This sort of things depends on an unbounded number of parents. You need some form of aggregation. If you think about how to represent this as the Bayesian belief network, you find out that there's an unbounded number of parents. We have to solve that problem in terms of aggregation. And there can be much more structure about individuals, about the relationships amongst them. The carry of some digit depends on the carry of previous digits, right? The probability that two authors collaborate depend on whether their papers authored together. So we're going to have a whole lot more structure we can have amongst the individuals that we also want to exploit. So here's an example of aggregation of someone shot Y depends on all the people who could have shot Y, all of the X's who could have shot Y, so you get shot if someone's shot. And so this is essentially an OR of this. And whether X shot Y depends on whether there's a motive opportunity and there's a gun, and the gun, whether X has a gun doesn't depend on Y, but the motive and opportunity does. This is the sort of simple models, sort of a simple version of the models we're building. One of the things that was also happened, you can view this, is you can also do, there's a whole lot of people who work in so-called non-parametric Bayesian model who use essentially the same models as this. And you might want to learn theta, the parameter for coin tossing, given a whole lot of observations of tosses, and you can build it as this IID assumption is exactly this plate model. So this plate model represents the IID assumptions that says each toss is independent given the parameter. So, and then from observing the coin tosses, we can update the parameter. So we get a so-called beta distribution from this. So what we're going to try and do as well as we actually don't really know how to do this, is to say that there is only inference, right? If we're going to do learning, it's just inference in these sort of plate models when we get big enough models. All right, okay. So what I'm going to do is I'm going to first of all talk about these probabilistic logic programs, which is trying to say that there's a whole close relationship between these parameterized Bayesian networks and logic programs. They look nothing like each other from the start. We'll actually find out there's a very close relationship between them. Okay. So what we did is, this was something that I did a long time ago now. So it's a language for relational probabilistic models. And we're going to combine logic and probability, where all uncertainties handled in terms of Bayesian decision theory, and logic specifies the consequence of choices. And so this independent choice logic theory consists of a choice space with probabilities over choices. I'll explain what this is in a second. A logic program that gives the consequence of choices. And so it started off with something around IJCAI 91, and now is the basis for this probabilistic programming language that's now become very popular, called Problog, which is developed in Leuven. So it's very simple. It's almost trivially simple. So there's an atomic choice is just an atomic formula. An alternative is a set of atomic hypotheses, and a choice space is a set of disjoint alternatives. And this is the same model as the axiom of choice. So you have a set of sets, and the idea is we're going to pick out one element from each set of the choices. So think about this like the axiom of choice. We have a set of sets, and we're going to pick out one element from every set. We're going to have a set of facts as an acyclic logic program that gives the consequences of the choices. In this one, we can include negation as failure. And we're going to have no atomic hypothesis in the head of the rule. And we're going to have a probability distribution over the alternatives of doing this. So let's give an example. The choice space here might be C1, C2, C3. You get to choose one of C1, C2, and C3. You get to choose one of B2 and B1 and B2. And for every choice, this logic program tells us what follows from it. So F is true if C1 and B1 is true, or if C2 and B3 is true. And then we have probability distribution over these alternatives. So these are just independent alternatives. So there's a possible world for each selection of one element for each alternative, and that's the same definition as you might have seen in the axiom of choice. You get to choose, from every alternative, you get to choose one element, and that becomes a possible world. The logic program, together with these selected alternatives, specifies what's true, and the elements of these different alternatives end up probabilistically independent. So it's almost so trivial that it hardly seems worth interesting with making everything independent of each other, unconditionally independent in a very simple logic program. We can do a whole lot of things with it. So here's the example before. We have the choices between C1 and C. You have to choose one element of C1, one element of C2. In each world, there's a logic program that specifies what follows in that world, and we have the probability of the world is just the product of things. So it's almost a trivial, it's a pretty trivial, simple logic, pretty simple relationship with everything being independent a priori. And this is a normal way we can get the probability of some hypothesis in here. And it turns out you can trivially wrap any Bayesian network into this language. So you can have any Bayesian network, this tampering and fire, for those variables without parents, like tampering here. We can write down the probability of tampering is 0.002. Similarly for fire. And for alarm, we're going to write it in these rules that for each case of tampering and fire, because alarm here depends on tampering and fire in this belief network, for each case here, we're going to have some independent random noise, some independent choice about which is going to follow, and they're the free parameters in the Bayesian networks. In a Bayesian network, you can specify all of these free parameters, and you can have probabilities associated with them. So although it may look a priori independent, the parameters of the Bayesian network correspond exactly to these choices that we're doing. So when you specify in a Bayesian network particular numbers, they're going to correspond exactly to these choices about what we're building in here. Rules, so we can not only represent Bayesian networks, we can also represent decision trees with probabilities. So conditional probability of E given A, B, C, D, there's a mapping between rules and decision trees. So in here we could have a decision tree which says when A is true and B is true, you end up with this right-hand 0.7. That's saying that E is true if A and B is true, and this H1, and H1 has probability 0.7. So decision trees also correspond to sort of simple rules in here. But now we have plates. Before it, they correspond exactly to logic variables in Prolog. So when we had plates before, and you can represent this grades depending on the intelligence of the students and the difficulty of the course, is this reasonably simple logic program of now we could actually talk about how grades depend on intelligence and difficulties and other variables. And this might seem as though it's, why would anyone want such a bizarre language to write Bayes nets? Well, here's an example of doing this. So here's the variables that the Zs depend on the student knowledge, time, and Z. So this is the example we saw before with parameterized random variables. And here is my complete axiomatization about how Z depends on its parents, nose, carry, X, Y, and Z. And if you look at this first one, it says that some Z depends if z has some value v, if x has some value for digit and problem has some value v of x, y has some value v of y, the carry has some v carry. If they know addition and they didn't make a mistake, then it's just the normal value we saw before. Right? If you look at the top right one, if they know addition and they did make a mistake, we're going to select a digit at random. And if they don't know addition, then we're also going to assume this model they're going to select the digits at random. We don't have to select digits at random, but essentially saying there's an axiomatization of the cases. The case here is the only cases are that they either know addition and they didn't make a mistake, they know addition and they did make a mistake. And so these random choices actually have nice meanings in here. We have probability distributions over that they made a mistake or didn't make a mistake, and probability distributions over digits that they're going to select. So it turns out that this is sort of a reasonably nice language for people to sort of specify sort of relational probabilistic models. So what I'm going to do is I'm going to talk a little bit about some work that's been going on sort of since 2003 on lifted inference. Before we do that, we have to introduce how inference works in Bayesian networks. Here's a Bayesian network. What we're going to do is the probability of some query variable E given G is the probability of E and G divided by summing over out all of the elements of E, some normalizing constant on the bottom. And so all we really need to do is this probability of the E and the G. To do that, we're going to add in all the other variables. And when we've added all the other variables in, we can decompose into this product. And if you know how to and so we end up with having this probability of this A, the probability of B given A and C, the probability of C, the probability of D given C. We're going to add in all those variables, then we're going to sum them out. And what the trick is for doing this is that we're going to distribute and sums over products. That's what we're going to do. We're going to bring in the sum. We're going to, if you look at that sum over D here, when we have the sum over D, we're going to everything that doesn't depend on D can be distributed out of that sum. And so if you do that, we're going to find out the only thing that depends on D is the probability of D given C times the probability of E given G and G given E and D. We can distribute out again A. The only things that depend on A are the probability of A and the probability of B given A. The only thing that depends on C now is all of these things. It's all of these things, but this other one, probability of E given B, can be distributed out, and the probability of F given D, E. So it's just really distributing things out, and this is, if you want to do exact inference in belief networks, variants of this are the state of the art about how to do inference. They will exploit the structure. For those who know, it's, the algorithms here are exponential in the tree width, which is a structural property of this Bayes net. But what we're going to do is we want to do something more than that. We're going to do it for these relational probabilistic models. We want to treat individuals about which we have the same information as a block. We're just going to count them. And we're going to use both lifted theorem proving ideas. There's no need to ground them. We're going to do work related to sort of theorem proving. And it's going to be exponentially faster in the number of, we'll say now there's the potential to be exponentially fast in the number of individuals who are not differentiating. But it relies on knowing the population size. And so one of the first algorithms to do was called first order variable elimination. And what you could think about this is you could start with one of these parameterized belief networks. You could go to, for first order variable elimination, we could get to a parameterized posterior, and then we can ground that out, means replace the variables with constants and get to a posterior, which is going to be the same as if we grounded them to a belief network and then we did some other algorithm like variable elimination to compute the posterior. So here's one of the silly examples I made up. Suppose Joe has purple hair, a purple car, and big feet, and with purple hair, a purple car, and was very tall, was seen committing a crime, and you want to know what's the probability that Joe is guilty. And if you think about this for a while, you realize, well, it depends on how many other people have this property. How likely is it that random people have purple hair, purple car, and how many other people there are? Right? If this is, you might say, well, if it's 1 in a million, then it's very unlikely. But then if you think about it for a while, you think, well, there are four type people like this in Vancouver, right? So once you start getting large populations, things, even very unlikely things, there are still multiple people who have things that are true. So a reason about here, it depends on the population size. right? If you were in New York, there'd probably be lots of people with these properties. And so what we're going to do is to build on work in sort of theorem proving and unification. So in 1965, Robinson showed how you could do unification allows around many ground steps with one step. So if you think about, if you know unification, you have f of xy or h of xa, and you want to resolve that with h of by or g of yw, you unify h of xa with h of by, and then you can say that x becomes b and y becomes a, and so you have f of bz or g of aw. And we have this most general unifier. So we can do a whole lot of ground, we can do a whole lot of what's previously ground steps in a very high level in which one step. So this is the basis of something like Prolog, of doing it in Prolog. Now if you try this with multiplication like for our parameterized belief networks, so they're parameterized factors, it nearly works. Right, f of x, y, and h of xa, you can multiply this, you can unify them together, and you get some factor on h of b of a. And it works in the sense that if you have these two variables and you multiply them out, you can actually do this in one step. It doesn't quite work because the first parameterized factor you can't subsequently use it for x is b. We can use it for other instances. So although we have unification here, we need to not just apply it, we need to actually start splitting things. So you can split this f of xz and h of xa into these two cases, f of bz and h of ba, and f of xz and h of ax. So we're splitting into these two cases, one of which x equals b and one of which is x is not equal to b. So we're going to divide them up into two different cases. So we're going to start effectively doing a case analysis when unification becomes case analysis and splitting. So there was lots of work before on people doing inverse unification and all sorts of weird things because of problems like this, but it turns out to be much simpler of just splitting. And then we can define things called, so inequality constraints sort of fall out of unification. So inequality constraints are the sort of things that we're going to end up with in here. So I'd like to reason about case analysis through unification, and we end up with these parametric factors like if x is not equal to c and interested x or boring, then we're going to have a table of interested and boring in this value that's parameterized by x. But because of unification in here, we're going to just talk about some other individuals. How am I going here? All right. And so here are sort of cases we're doing. So here's an example of whether the person's boring influences whether each individual is interested, and whether someone's interested influences whether they ask the question. And I've observed no questions, and what I want to do is to work out how many people are, whether I'm boring or not. Okay? Because no one asked any questions, I don't know why. So what we can do here is we can eliminate interested here, and we end up having this, we end up with a factor that says that boring depends on interested with some t1, interested is a factor by itself, and we're going to eliminate boring, and we can just do pointwise to the power. We can actually do this completely liftedly. We can just, it's composed pointwise, we can do it in constant time. So although we have a Bayes net here that's in size n, we can actually do inference of summing out inference and summing out asked questions. We can actually do it in constant time. So although we have the grounding of this is linear in the size, and typically they're polynomial, we can actually do inference in constant time using this. Another case we can do is if we want to sum out boring, well, in variable elimination, there are n random variables, all of which are completely interdependent. And so the smallest factor is this factor on all of these interested, and it's of size 2 to the order of d to the n, where d is the range of all of these that are interested. So if you think about doing this in the grounding, it ends up being exponential in n. But we can exploit this exchangeability, the fact that we knew the individuals, we're not going to, only the number of them matters. You can just talk about the number, we can do it for the number of interested the number of interested individuals have a value there, and we can have n of these. The complexity here just becomes now to polynomial. So now we've gone to exponential to polynomial time by exploiting the fact that we don't need to treat each individual separately, we can just count them because they're all exchangeable. So we're starting to now, instead of treating each individual individually as an individual, we're going to just count the number of cases that we're doing it because that's all we need to do. And so we can have lifting reduces from polynomial to logarithmic or even constant, exponential to polynomial in the population size of the undifferentiated individuals compared to ground. So that's what lifting does. We now know we can lift all unary relations. So if you only have arguments of a single argument, we know how to lift all of those. We know how to do. We know we can't do all binary relations, but we can always be exponentially faster than grounding. So it's sort of one of the very surprising results in computer science. We can always do exponentially better than we could by doing the naive way of doing things. Currently, the most efficient algorithms compile to some secondary representation, do case splitting. So for example, Mayran has compiles to C++, and it's so much faster than other algorithms for doing lifted inference, and even just normal probabilistic inference. In fact, we can do these algorithms now so much faster than we could before. Also means there's lots of potential for approximate inference. So the games people, so now we can do, most approximate inference schemes are based on exact inference schemes. We can now do exact inference so much faster than we could before. Now there's a whole lot of interesting work to do an approximate inference. How am I going here? Okay. So what we'll do now is talk. So now you might think, well, these are just sort of big these are just sort of big models, and maybe they're not really any different to the ground models. What I want to do now is try to convince you that these are very different to the grounding, to the normal models. And so here are three sort of simple models. So the first one is naive Bayes. So Q here, so the R's depend on the Q in the left-hand one. A, this is called a naive Bayes model. So in B, the Q depends on R of X. And in the right-hand side, this Q depends on, is an undirected model where Q depends on, where this Q is just joined with R of X. And these correspond to these three grounding models here. A is a naive Bayes. B, we're going to make it something called a relational logistic regression in a minute. And C is this ends up being a Markov network. So we end up having these three directed models, either naive Bayes or this directed model with lots of ancestors, or this Markov network. And if you actually study the independence assumptions of this, A and C actually have the same independent structures. So A and C is this naive Bayes model of actually has the R's are independent given the Q's, but are dependent not given the Q's. And this directed model in the middle has some quite different dependency structures. So we can start studying how these models relate. And some things, even familiar friends like logistic regression that I'm assuming people have heard of. Right, this is the same thing about how a neural network depends on its parents. Logistic regression says that this Q of R1 to Rn is the sigmoid of these weighted formulae about these weighted formulae of R1 to Rn. And the sigmoid here is 1 over 1 over plus e to the minus x. And so this is the familiar logistic regression. If we have exchangeability, then all the W's have to be the same. So Q of R1 has to be, so all of these R's have to be the same value. So we're going to have sigmoid of W0 plus W1. And everyone's happy now, and everyone thinks it works because logistic regression is simple and works. And if you're doing a logistic regression, you can say, well, you could say, well, do we represent true, false as 0, 1, or plus 1 and minus 1? And of course, the answer is it doesn't matter, right? So if you can, it doesn't matter whether you represent 0, 1, or minus 1 and 1. It doesn't matter for the R's whether it's true. But it turns out that's not true for relational, if you have the relational model. Consider the case if we're learning the parameters for n as 10, and we'd like to predict for 20. So we're learning a population for a small population. Typically, you learn things for small populations, you want to apply them to big populations. right? So that's the typical game we're doing here. And so what we'd like to do is, it turns out that it depends on how these, where it's an arbitrary decision for normal logistic regression, it turns out here it's very dependent on how it grows depends on the representation of true and false. It's just, in some sense, it's for people who are sort of just so familiar with logistic regression, this just seems bizarre. So if true is 1 and false is 0, then the probability of Q given R1 to Rn depends on the number of R's that are true, right? Because falses don't get anything. If true is 1 and false is -1, then this probably depends on how many more R's are true than false. So it doesn't only depend on truths, it depends on how you can combine the true and the false individuals, essentially because n is not fixed. We want to build a model that works for all n. If we have some other model like 0 is true and false, it depends on the number of R's that are false. Right? And so if you have applying learning for 10 and learning for 20, how it grows all of a sudden depends on a seemingly arbitrary choice about how this works. And so what we've done then is we've sort of said, well, and there's a whole lot of other formula not based on these logic programs, but based on sort of weighted formulae. So we have this weighted formulae which has a set of logical variables, a logical formula and some weight, and here's an example. The weighted formula here, we're talking about whether, if you go to a party, whether it's fun for you depends on whether you're friends. So whether it's fun for X depends on whether their friends are social or their friends are not social or antisocial. Right, so here's the model, so here's this weight. So there's a weight X and a weight XY. And you have this, so you have variables, you have a logical formula, and you have weight. And then we're going to assign these individuals to these variables. We can have these worlds or assignments of values to each ground instance. There's a whole lot of models that are undirected models, particularly called Markov logic networks, which are undirected models where weighted formula defined on measures on worlds. So this is the Markov logic network corresponds to an undirected model where it has these weighted formulae. We've been developing this model called the relational logistic regression, which is a directed model where the weighted formulae are used to define conditional probabilities. So we can have this dual for this. And if you include these formulae, then the conditional probabilities end up being exactly these logistic regression formulae. You can count not just on the number of things that are true, the number of things that are the number of friends you have, but you also have to work out with the number of friends who are social and number of friends who are antisocial and how they mix together. It turns out that, so we've got to count the number of friends who have this. And we can actually have weighted formulae. We can completely characterize this as arbitrary polynomials of counts. So we have these polynomials of counts. So we can represent all of these things. So the probability of directed models can be interpreted locally. They're modular. Adding a dependent variable without side effects is straightforward for these models, but turns out to be impossible for Markov logic networks. David Buchman had a nice paper in AAAI this year that was talked about how it's impossible to add these to things like Markov logic networks without having side effects. It's something that the people have used these for a long time, but very few people look at what you can do and you can't do. You can prune in inference. They require the structure, the conditional probability to be acyclic for very technical reasons, but maybe not with working on ways to handle that. So noisy OR aggregation corresponds to logic programs with layered logistic regression. We're thinking about, can we get sort of some relational neural networks, right? We'd like to condition on some relations in the world and then build up these models that are more like, these neural networks can be seen as these cascaded logistic regressions. So we're trying to build up models that are relational versions of that. All right, for the last few minutes, I'm going to talk about things we have no idea how to do. Okay, let's skip through some of these. So we're going to talk a lot about what's called existence and identity uncertainty. So if we're talking about here, we have a whole lot of symbols, we have individuals in the world, we'd like to work out whether things exist, whether things don't exist, and the correspondence between them. So here's an example of something like that. We'd like to have a model of what whether Mary likes an apartment depends on whether there's a bedroom for a daughter for Sam, whether Sam's room is green, whether there's a bedroom for Mary, whether Mary's room is large, and whether they share. So it's a sort of thing we'd like to, a relational model about objects and relationships. And what ends up happening is you can do all sorts of things like models about which room Mary likes and which room is Sam's. We build all these nice relation models, and we turn out, how can we condition on this particular apartment on the right? And it turns out to be a really tricky problem. I still think we don't know how to solve this. We don't know how to solve how to give a general description about the world and a model, because it depends on which room Mary chooses and which room other one chooses, and we need to model a whole lot more. There's a whole lot of plate notation we can do, but there's a chance that they're going to share a room. There's a chance that these objects that we assumed were different, well, maybe they're actually the same room. So we have to reason about identity in these things, and so when they have to share. Another example is examples of radar following aeroplanes. We can talk about whether there is no plane or there is a plane. So you get radar blimps, and we have to work out whether we observe a blimp, you've got a hypothesis that there's a false alarm or there is a plane. And so if you observe another blimp, and there's a plane before, it's either false alarm, it's the same plane, or there's another plane. So we end up with this cascading individuals that may or may not exist. And so we have to reason about not just assuming we know what exists or not, but we have uncertainty about what exists. And it turns out that actually I'll skip this one. Just to conclude now, in other things that they're doing is, turns out these probabilistic logic programs were the first probabilistic programming languages, and they're now sort of recognized as the first probabilistic programming languages. Probabilistic programming languages have become trendy recently because of this big DARPA project. Another issue is that data is now being published with respect to formal ontologies. So municipalities and governments and scientists are being forced to publish papers with respect to formal ontologies. How can we build models that interact with data that uses such formal ontologies? We'd also like to publish hypotheses that make probabilistic predictions so they interoperate with this data. We'd have identity uncertainty, the probability of equality. So for example, this is a problem that Google Scholar faces. We'd like to do these citations refer to the same publications. And then we'd like to interact with utility models and represent actions and times. Okay, so in conclusion, the field of statistical relational AI studies how to combine first-order logic and probabilistic reasoning. There are three challenges. One is in representation. We want what John McCarthy called heuristically and epistemically adequate representations. So are they adequate? Can we actually solve problems with them? And can we actually represent problems with them? And we'd like to do this for the models plus observations. And we also want to model causation and actions and utilities and ontologies. We'd like to do inference. We want to exploit both the structure like efficient Bayes net algorithms do, and also exploit exchangeability. We want to compute posterior probabilities fast enough to be useful. We'd also like to do learning, which is find the best hypotheses conditioned in the observations, but for us that's just inference, right? We're just going to condition on, we have enough database, we actually just condition on, and it ends up being inference. And I found this wonderful quote from Bertrand Russell about what's now required to give the greatest possible development of mathematical logic is to allow the full importance of relations. And defined on this a new secure basis of philosophical logic. So that's 100 years later, but we're now finding we're building on relations in order to build on top of all of these other probabilistic models. Okay, and maybe we can get to we can achieve, with respect to the greatest ages of Greece. So that's what we're going to hope for here. All right, thank you.
Thanks, David. So we have time for a few questions. People have to leave, I understand it, but tour de force.
Just have you guys on.
Sure, there are questions.
So when you were talking about the ICL, language, I guess the process is to be able to go from a belief network to a logic program, or in general, maybe to go from any graphical model, a holistic graphical model, to a logic program.
Or you just write a logic program. Or you just write the logic program.
Yeah, so actually this is already my question. So what is the benefit? I mean, I understand you can do it, and maybe you can go back and forth between the two representations. But what is the benefit
Of writing the logic program.
of being able to?
Well, the logic program is sort of very simple. If you're interested, if you're used to the logic programs, it's very simple to write this deterministic system that depends just on these independent choices. So and it turns out it can represent an arbitrary Bayes network. So the whole thing about the probabilistic programming is you effectively the same thing. You have these independent choices plus a deterministic system. So that's the basis of all these probabilistic programming languages that people now write because they're very flexible languages of representing conditional probabilities. I mean, you don't want to write conditional probabilities as tables, right? You want to write them in some more flexible language. The logic programming is one of them. Probabilistic programming is another. These relational logistic regressions as ways to actually effectively write conditional probability tables. It's also relational, so we could actually talk about multiple relations.
Other questions?
Can you talk about objects whose existence is conditioned on another variable taking a value?
Yep. Is that a question?
Yeah.
Yeah? Yes.
Like, does that fit into like the lifted inference scheme and things like that?
Well, we haven't done, with lifted inferences really only work for these very simple sort of Markov logic things. But the languages that we have, which we do grounding for, end up having these variables the individuals whose existence depends on the values of other variables. Yes. So when we talk, we're trying to get these sort of rich languages and then doing efficient inference on it. There's still a big gap between what we can really do efficiently and what we can't do. But we really want to talk about these objects and relationships and all sorts of things that depend on other things. And so we want to condition on, but often these algorithms, the efficient algorithms actually do conditioning. So you condition on things and then you work out under whether something exists, you have some other property, and when this is property, you don't have this existence. And you're searching through these spaces. I don't know if that helps, but.
Is there another unit of operation you can use besides conditioning to give you efficient inference algorithms?
So the algorithms the most efficient Bayes net algorithms, exact ones, things like are based on something like recursive conditioning. And so you can condition, you represent, you can recognize when graphs are disconnected, and you can also cache things you've already computed before. Together, those three things get you efficient inference. You can do it in times of linear in the tree width. So you can do efficient inference with those three things. So you want to recognize disconnectedness, you want to condition, and you then want to, and then you have to cache things you've already computed.
I'm just wondering about like the submodularity results, or if you have like continuous networks, maybe there's other things you can do. Where you can if you have continuous networks, you can do other things. This is for these discrete type problems we're doing this for. Yeah, there's an unbounded number of things we could do. I mean, we've only done lifted inference for discrete, effectively these Markov logic networks. And some things for these, from some aggregation models, we also have lifted inference models for them. Yeah, we don't know how to do, there's some people doing continuous variables, but then they're often just sort of things like mixtures of Gaussians. They actually have nice lifting properties because they're only pairwise. So although you have a property of arbitrary number of things, they're only pairwise.
I think at this point we'll call it a day. I just want to thank David for such a great presentation. It's such a coherent research program. It takes us right up to the current age of research, what we do and what we can't do in particular. which is really a great way to end, I think. And David actually is now just writing a new book, I think, what I heard, on logic, probability, and computation. Is that right?
Oh, well, yeah, the book on this is coming out in, we just signed an agreement this week, so.
Pretty exciting news. Anyway, let's thank David.
I'm also going to teach 522, which is all about a lot of these things, so.
Problemas